So the first one seems interesting. And one question that we can ask ourselves is, can more data be the only solution? If I'm just retrieving more and more data, I'm Doodle and I'm retrieving all the data on the planet, maybe I can just use nearest neighbor classifier to achieve any test. And you can see that in 2D, it's something that we can see clearly the boundary of the real data distribution that will fit to the boundary given by this model. And in fact, yes, in low dimensional space, the boundary will converge to the real data distribution if I have enough points. But what does it mean having enough points for videos, for images? And in practice, it's no. We cannot expect just to use millions of videos and nearest neighbor to have a good classifier, because here the important thing is that I cover the whole domain space with enough data. And so it's a problem of covering the input space with enough data. So here data is necessary, but it's not sufficient to solve the problem. And to see it, because I want to cover my input space with enough data, so that let's say here I want to have a maximum distance between any new point that I can receive in production and the point I have in my training set. I want the distance to be smaller than 0.1. The largest distance between any 2 points must be smaller than 0.1. In 1D, if I have a domain space which is a unit 1, I will only need 10 points. And if I receive 1 point, the nearest neighbor will be closer than 0.1 to here. If I go to dimension 2, I will need 100 points to cover very well my domain space. And if I go to dimension 3, I will need 1,000 points to cover very well the domain space. And so this is called the curse of dimensionality. The number of examples required to cover well a space is exponential in the dimension. Here there's a minus because the epsilon is between 0 and 1. And we will use this formula for the most simple data set in Vision, called MNIST. So MNIST, it's a tiny image. It's this one as an example. It's 28 pixels by 28 pixels. So I have, and it's just black and white pixels. So I have an input space of 784 dimensions. If I want to cover uniformly the input space with data, I will need at least 10 to the power 784 examples to cover it, which is a number that we cannot even imagine in our head. It's probably more than the number of atoms than in the universe or something like this. So no, more data will not solve the problem. But you can also ask yourself, yeah, but what does it mean to cover uniformly the input space of 28 by 28 pixels images? If I just take one random point in this space without any constraint, the probability that I will have one digit of MNIST is close to 0. If I just sample uniformly in this huge space, having really a sample that is close to a digit is 0. So I have two different things. The nearest neighbor model requires to cover the whole space uniformly, but on the other hand, only a small part of this space is really data that are probable. And this is the manifold assumption that is very important in machine learning. We represent our data in space that are too high dimensional. We have too many degrees of freedom to represent all possible images. And in fact, the data that is useful for your task is only a tiny, tiny part of it. But it's super hard to represent this tiny part in the space. And this is what is a manifold. In a 3D space, a manifold is a surface, And so the number of degrees of freedom over a surface where I can move on the surface is 2, and the ambient space where the surface is living is 3. But here we have space in hundreds of dimensions, and probably the data manifold is a much lower dimension space. And as an example here, I take a photo of myself, and this image lives in a 2 million dimensional space because I have 900 by 700 times 3 RGB channels numerical value. But really, the system that will generate all possible images of my face is only 43 degrees of freedom. It's the muscle that I can use to generate different shape of my face. And you can see that 43 is much lower than this 2 million. So it's only to give you the intuition that data live on lower dimensional space, but they are represented in data in high dimensional. So can we think about a hypothesis class that will find these low dimensional space, these manifold? And this is the expertise in machine learning and deep learning. According to the dimension of your data, you will look at the data, you will maybe do some visualization, do some preliminary analysis with simple model. You will see at some point that you will need models with a given complexity. This is something that you will acquire with practice, with a lot of experiments, with reading on the scientific paper or reading the blogs. But at some point, you will see that probably if I use this kind of model, it would find the low-dimensional manifold more easily. And this is why you are here this week, to see some of these models to learn these manifolds. And if we want to interpret deep learning in this framework, it's a powerful way and an easy way to define the hypothesis class H. You will see by using TensorFlow or PyTorch, you can design architecture that are very complex. And these architecture will have parameters. And the space of the parameters of this model will be this H. It will be your hypothesis class. So as soon as you are fixing the architecture of a model, you can think that you are fixing the hypothesis class here. And there will be an optimizer, which is an iterative algorithm that will start at some point that is associated to the initialization of the parameter of this architecture. So we will initialize the parameters randomly. We'll land somewhere in the parameter space, and the optimization will move in the space H to find the deep learning model that will minimize your empirical risk. And if you restrict the way the optimizer can move in this space H, you are doing some kind of regularization. Maybe you will say, this part of my space H is very complex. There are very complex models that can easily memorize all my training data set. I will put some boundaries so that my optimizer will not be able to explore this kind of model in the space H. This is called regularization.